Hello everyone. In this video we are going to talk about some important points about creating meshes in ANSYS, because you know that the method ANSYS is using is based on these meshes and these elements. So if the meshing is not basically efficient and you do not have sufficient number of elements, then you might not represent the geometry using these elements well, and you might not have accurate results as well. Sometimes your computations might take a lot of time. So are there specific things that we can keep in mind when creating the meshes and performing basically FEA analysis using ANSYS? And yes, the first one is, if there is any symmetry to the part, try to take advantage of that. For instance, let's take a look at this part here, which I used in one of my previous videos. Let's say this is the part that you're going to do any analysis on, right? For example, you fix this interior edge, and then you applied a load to all of these three edges, okay? To all of these three. So the part is completely symmetric. Or maybe it's just symmetric about one of the axes, x, y, or z, right? The planes, x, y, x, z, or y, z planes. If there is such a thing, take advantage of that. And instead of creating mesh for the entire object, then just create mesh for a portion of the object. So let's say here, the xz plane is the plane of what? Symmetry. So this object is symmetric about this horizontal axis. Then instead of creating the mesh for the whole object, what I will do is I go to Tools and then go to Symmetry. And then here I say the symmetry plane for me is XZ plane. And then I apply that and then I generate. And look, half of the model is gone. So now I would only analyze half of this model, right? And of course, it is going to take less computation. So taking advantage of symmetry in parts that have planes of symmetry or axes of symmetry is extremely time-saving. The other thing is, if there are details, small details, that do not affect the behavior of the part, try to remove them. If they have no major effect whatsoever, unless say the stress final results, then just get rid of them, because those small elements means for ANSYS that it has to basically create specific size elements, smaller size elements, change the shape of the elements, rotate them, distort them, and so on, to be able to cover those small details for you, right? And that means ANSYS is going to have a harder time creating the meshes and also solving for the equations and analyzing the results and post-processing the results. For instance, let's say you want to do stress analysis on this simple cantilevered beam, right? And one of the things you have are these fillets here and on this other edge on the other side. Okay, so the question is, if I remove these fillets, these small details like these, is that going to affect the stress results in my object? The answer is no, because these are external edges and they are not locations of a stress concentration like these edges are, like this one here, right? This edge here is where this intersection is where the concentration of stress can happen. So having a fillet over there does make a big difference, right? So I'm not going to remove a fillet if it's over there, but if it's just here and it's an external edge, there is no major effect from this on the stress results. Why should I include that? Because the method that I show you I'm going to use, if I can, is using basically what we call the hexahedron elements, which are, they look like this, they are like cubes. And if I have those fillets, it's going to be a very hard time for ANSYS to fit those elements with flat faces to a curved surface like this. It would either fail and replace them with tetrahedrons, which they have some disadvantages compared to hexahedrons, or it has to use very, very fine meshes over there, while in general, for this top flange, it might not necessarily need to use very small elements. So if there is such a thing, go ahead and delete it, right? And you can use the tools in ANSYS. If you already made it in ANSYS, you can just go ahead and delete them. If you brought it from another CAD software, there are tools in ANSYS in Design Modeler that you can go ahead and delete a surface. Okay, or sometimes there are different radii, not necessarily even sometimes different radii, but different fillets, but they are separate from each other. And you can join them together and merge them together to reduce the amount of different types of elements that you need. So if I can do that, I would do it. Or let's say here on this surface, I have some small cut, right? Or some small extrusion, which is what? Which is, for example, the logo of the company, right? So I have some name here, extruded or cut extruded, especially extruded, and that is not going to affect anything. So instead of me having that small detail being a part of the finite element, I would take care of that. I would remove that and try to only take to my meshing workbench and to my analysis workbench what matters in terms of the analysis. Okay, all those minutia's, just get rid of them. So this is the first two things, right? Remove the details, take advantage of symmetry. The third thing is they always say that one good solution, if you want to, one kind of like general solution, if you want to get better results, more accurate results, is to reduce the global mesh size and reduce the number of, increase the number of elements or reduce the size of the elements. Now, the matter of fact is, yes, it can most of the time create more accurate results. Not necessarily always, and sometimes it might not necessarily improve what we call mesh quality. And what is mesh quality? What are the metrics for it? We're going to talk about them right after this. So it's not a general solution for all problems of finite element and meshing. Hey, use the smaller elements. That's not necessarily the case. Another thing it can do is it can create large unrealistic stress values. It can create what we call stress singularities, because you are applying a force right on the top of an element that is very small, so the amount of stress over there tends to go to infinity, and those unrealistic stresses are something that can easily throw you off when you're looking at the maximum stress values, right? Somebody who has no knowledge with finite element, when they are looking at the safety factors and trying to design, they might look at some very large number in maximum stress. And while it does not make sense theoretically to have such numbers, but they just trust the software because it had generated such big numbers. And they don't go and look, hey, right above a very small element, I have applied a huge force, a local force, and that causes a singularity. So you have to be very careful about that. One of the things you can do is adaptive mesh refinement, which basically keeps reducing the size of the mesh until your results start to converge. So you start with the larger mesh size and then adaptively reduce it until you see the values of your stress or deformation or anything. They start to converge and the change in them gets smaller and smaller. Then you say this is the good mesh size. It's called adaptive mesh refinement, and I'm going to show you how to do that in this video. The next thing is local mesh refinements. So for example, if you have this structure and you have locations of stress concentration, around these areas, you need to use a smaller mesh to get accurate results. But for the rest of the beam, you don't really necessarily need very small mesh size. So instead of bringing down the global mesh size, you're going to keep the global mesh size at a reasonable number, but around these areas that you need smaller mesh, you apply something called a refinement and use a smaller mesh size. which you can do with tetrahedron elements. So that will keep the number of elements at a reasonable number, so the computation is not long, yet still give you relevant results and relatively accurate results. So let's go ahead and show you these items 3 and 4, right? The adaptive mesh size, the global mesh size, and the refinement. And then we start talking about the quality of the mesh and the metrics for that. So here, this is my mesh, okay? And let me go ahead and create some mesh. So here, if you click on the mesh, you see there is a sizing here, right? And I'm allowing for adaptive sizing to happen, but I have to activate it, and I'll show you how exactly we'll do that. But if I go ahead and right click and say generate mesh, okay, and then if I right click, this is the mesh that it created for me, and here it is using tetrahedrons. And you see around my areas of concentration, the mesh size is not smaller. So some of the things I can do is this. I right click here and insert and go to sizing, and the geometry is going to be the whole object, and the default size is 25 mils. So I'm not going to reduce this to like 5 mils or 2 mils or something and make the number of nodes extremely high, right? And keep it at the reasonable. So instead of 25, maybe I make it 15, right? Make them a little bit smaller. This is the global mesh control, right? And update the mesh. So you're going to see the mesh goes down in size. I get some more elements, right? Which could be enough for, and we'll talk about when it's enough or not, but around these areas of concentration, what can I do? So this is what I'll do. I right click here and say insert, and then say I want a refinement. It says where, and I say in these 4 areas. I want you to apply a refinement for me. And now look what happens. You see? So now clearly I have what? I have smaller mesh size here compared to here or here. And that way I'm still able to get accurate results, but the number of nodes is not basically skyrocketed because the global mesh size I have not changed. So this is what? This is the global size, and this is the refinement, local mesh. But as I said, we can do adaptive size control. What does that mean? So here is what I'm going to show you. And here we are going to apply a fixed support on this end, and we're going to apply some force on the top end. So here, when we go to the solution, typically by default, this number is 1, max refinement loops, and I'll talk about it. So let's say here, what I want to see is insert, and I want to see total deformation, and I want to see some stress, right? So let's say I want to make sure the deformations, which are basic calculation for everything else, I want to make sure these deformations, they would converge. Converge to what? Converge to the actual solution. So I right click on this total deformation and I say insert, and then I say insert a convergence for me. And it says, okay, how much is the allowable change? What does this one mean? Means between one iteration to the next, if the change in the deformations of the nodes, in the displacements of the nodes, U, V, and W, the 3 different directions displacements of the nodes, if they are less than 20%, the change in the values compared to the previous iteration, if it goes below 20%, I assume the convergence has happened. But 20% is a big number, right? It means I might not exactly be there. So instead of 20%, I change this to 1%. I say when my results are not changing more than 1% between one iteration and the next, then call it what? Then call it convergence. And then go ahead and solve this and see what happens. So if you look at the convergence results, you clearly see in one refinement loop, it could have reached about 0.1% last change. So it reached even below the number that I asked, right? So that means it was really converging. Now, if I bring this number down and say, hey, I want you to go to 0.05 or something change, right? So very small change from last time, then this is not going to converge in one refinement loop. So I need to go to the solutions and change the number of maximum refinement loops and say maybe 5 or something, right? Because now my threshold for convergence is way smaller, and then let it solve it again. Okay, and you see after several minutes, finally after 3 refinement loops, it could converge to 0.02 instead of 0.05. And if you scroll down here, you see that the number of elements that we have used, and you can see here in the mesh, the number of elements right now, if you click on mesh and go down to statistics, here you see the number of elements is 15,000, okay? So that's how much we have right now, but it kept going down until it reached about 601,000 elements. And that is where you see the results are not changing. But if you look, for example, if what you care about is only up to 3 decimals, right? Then once you went from 15,000 to 61,000, right? The number of elements were like 4 times more. Then you have reached already what you needed to reach. Okay, so you really do not need to go all the way down to here if you don't want to go to 0.02% change, right? Or 1% or something. So maybe 3 decimals is good for me. So I would just bring down the total number of elements from 15,000 to 61,000. So change this body size, right? And as long as I'm in that area or a little bit more, I should be good. For example, if I change it to 10 this time and redo it, right? Remesh this part and look at my statistics. So if I look, you see right now I'm at 34,000 with that kind of size, right? So that was 61,000. So probably, I don't know, something like 7 or so might do the job. Now you can calculate it exactly, right? Because it's a cubic factor. When you are changing the size down by a cubic factor, the volume would change and the number of elements. But here I'm just doing some rough estimate of what global size might be good in this case. And let's just see here, I'm at 79,000. So probably even maybe 8 mils would do the job in this case. And I don't need to go any further down. Yeah, you see here is about 59,000. So I'm very close, somewhere between 7 and 8, very close to 8 is probably where I can have my deformations converge up to 3 decimals. Okay, so this is the adaptive method. Now, when you generate a mesh, okay, and you get all these elements, not all of the elements are necessarily good elements. And how do we define element quality? So there are different types of elements that we use. Let me show you. So for example, for 3D objects, the elements we use are tetrahedron, pyramid, triangular, prism, and hexahedron. The most common ones are typically tetrahedron and hexahedron, mostly tetrahedrons. And when you have a tetrahedron in 3D, when all of the sides of this tetrahedron are equilateral triangles, that is like the perfect tetrahedron, okay? Or if I want to look in 2D, if I have a triangle, if it's an equilateral triangle, that's like the perfect triangle. If I have a quadrilateral elements, if it's a square, that's the best form. But the more the shapes are deformed from this ideal perfect cases of square and equilateral triangle, the less accurate their calculations become. So, and this is where the metrics come in, and these are the metrics for measuring the deviations of the shape of your elements from the ideal elements. One of the very common one is called aspect ratio, which is the ratio of the longest edge to the shortest edge, right? Which can vary anywhere from 1 to basically infinite. 1 is very good because it's equilateral triangle, and infinite is basically something very long like this. That is definitely not a good element because the calculations inside of it by interpolation through the edges, through the nodal values, is definitely not going to be accurate. Another one very common metric is called the skewness, which again, it measures how close to the ideal shape the element is, and it goes from a 0 to 1, with 0 being an ideal shape, right? And the way that you can define it is, for example, if I look at 2D elements, let's say I look at the triangle, is by looking at this skew angle. So what is it that I'm doing here? So here I have an arbitrary triangle, and what I'm doing is I find the midpoints of the three edges, so this point, and this point. Then I connect this vertex to the midpoint, and I also connect these two other midpoints together, right? So I draw this line connecting the vertex to the opposite midpoint, then connect these two midpoints together, and it forms four angles for me here, right? I might call them theta 1, theta 2, theta 3, and theta 4. And if it's an equilateral triangle, if I draw these lines, right? So this one, that is the median, it's also going to be perpendicular to the edge in front of it. And then here is the other one. If you look, all four angles are going to be 90 degrees. So if I subtract these angles from 90 degrees, all of the answers, all of the values here are going to be 0, right? Which means perfect. Now, the more this triangle is skewed, right, the more it is turned to one side, the more these angles would deviate from 90 degrees, right? You clearly can see here that I have two angles that are more than 90 and two that are less than 90. So when I calculate this absolute value of 90 degrees minus all of these theta i's, clearly your values are going to be non-zero. And what I can do is I can basically, because none of these thetas are going to be more than 180, right? It's impossible. They can be very close to 180, but never exactly. So the maximum that this absolute value can have is up to 90. So now if I divide the maximum of these absolute values by 90 degrees, then this value can be either what? Can be either 0, 1, or a number between 0 to 1. Right? Where this is the absolute value, not 190. So let me use a different color so it's not really confusing you. So these are the absolute values. Right? So again, if they're all 90 degrees, like this perfect case, then maximum of 90 minus each one of them is going to be 0. So you have a maximum of 0, 0, 0, 0, which is 0 over 90. It's still going to be 0, which is perfect. If I have cases where one of these angles go toward 180, or maybe two of them, then this maximum is going to be like maximum of 0, 0, 90, 90, which is 90. 90 divided by 90 is 1, which is the worst skewness. Okay, so skewness close to 1 is very bad skewness. Skewness close to 0 is excellent, perfect skewness, right? And the same thing can be defined for quadrilateral. This time, instead of connecting a vertex to the midpoint, you connect the two midpoints together, and then the same thing for the other one, and then you measure again these four angles. Subtract each one from 90, get absolute value to get a vector, find the maximum of that vector, and divide it by 90 degrees to get a value between 0 to 1. And if you look at ANSYS, there are so many measures and metrics for mesh quality. These are two of the very common ones, aspect ratio and skewness, but there are a ton more. And here, this table shows you basically a summary of some of these methods, from element quality to aspect ratio to Jacobian ratio to warping factor, parallel deviation, maximum corner angle, skewness, orthogonal quality, and so on. And you see the ranges for them. Some of them go from 0 to 1, some of them go from 1 to infinity, like this. You see here, there is no right end, right? Or 0 to infinity, or something like that. And if they are on this right side, they are the worst kind of mesh, and they are on the left side, they are the best. So for aspect ratio, you see 1 is very good, infinite is bad, and for the skewness, 0 is good, and 1 is what? A bad. Okay, so let's talk about the quality of the mesh, and I'm here back to what I had originally, which I said it's not a good mesh, but how do I say it's not good? Well, one thing was the convergence that you saw. The other thing is the mesh quality metrics that we just defined. Let's see how much they are, right? At least one of them. So if I click here on the mesh and then go down here to the quality and expand it, and then here you see there is no metric, so I can change it and say, for example, I want the skewness metric. And right now, the skewness metric, if you look, this is the distribution of skewness for elements. You see that I have a lot of elements that are more than 0.75, so these are definitely bad elements, and the average is 0.63. So I have a ton of elements that are not really anywhere close to that perfect tetrahedron. And the good elements should be here, near 0. So this is clearly not a good metric here. And you can see, if you go down, you see that, right, the average is 0.59, max is 0.99. You should not have elements that large, or at least if you have, they should be very minimal, right? So what you can do is reduce the mesh size, as I said, to definitely bring it down. So here I go ahead and, as I said, insert the sizing, and instead of that 25 mil, I changed it. Remember, we went down to 8 or 10 or something. Let's go to 10, for example, and then update the mesh, and we're going to look at this distribution again. There we go. You see, now it's completely reversed. Here, the mode is here, and you see on this side that I had lots of big values. I don't. If you look down here, now the average is 0.26. Remember, it was about 0.6, 0.599. Now it's 0.26, and the max is 0.85. Really, I do not even have anything about 0.9. So you clearly see that reducing the mesh size would increase the quality of the mesh, of course, because now I can cover all of the areas with finer meshes, and I can approximate the geometry way better without the need to distort the shape of my tetrahedrons here. Here, I brought down the sizing one more time. Remember, it was 25. I brought it down to 10 by a factor of 2.5, and the average of skewness went from 0.6 to 0.26. Now here, I brought it down one more time by a factor of 2.5. I brought it down to 4 mils. And now, if I look at the mesh and look at this distribution here, right, and look at the numbers, you see now the average is 0.22. It was 0.26. So you see, it's not like continuous reducing the size would keep bringing the mesh quality to higher numbers and better with the same rate. As you pass some size, the amount of change in the quality and improvement in the quality is going down because your results are converging and there is no need really for further reducing the mesh size to approximate the geometry. And your collection of finite elements is now very close to the actual geometry, so your calculations should be relatively good. So just keep in mind, as I mentioned, that just keep going down on the size is not necessarily always a good thing. It means a lot more computation. Sometimes it means the stress singularities that you have to avoid and skip. And you have to know when to stop reducing the size. And I showed you the convergence method, and I showed you a mesh quality metric to kind of guess when is it that we should not go any further down. So here I go back to the sizing of 25, right, where you remember that the skewness was about 0.6, right? This is what we had. And now I want to see if I do a mesh refinement, is that going to make any changes here for me, right? Well, actually here it is showing 0.4, which is good. So here I would add a refinement, see if it affects anything about my meshes, because here I'm adding more small elements. It's a matter of size, not shape. So would that really affect anything? Remember, that was the distribution, and now it should be quite faster. And now if you see, the average went from 0.4 to 0.395. So that refinement is really for local size. It's not about shape, where most of these metrics are. And so it's not going to affect much. It's the global sizing that has the effect mostly on it. And the other thing is the meshing methods, which has effects on the convergence of the results. So let's talk about different methods of meshing. And as I said, there are, for 3D, there are the tetrahedron, pyramid, triangular prism, and hexahedron. Tetrahedrons are rather obvious, but there are some other terminologies that you will see when you go to select a meshing method that I want to clarify for you. One of them is called the multi-zone and sweeping method. So what is that? So one of the terminologies you hear is sweep. Sweep is basically having an object that is sweepable, which means you can start on its surface, let's say on this surface here, you can start a bunch of what? A bunch of squares, and then sweep them, let's say, along this path, along this edge, and sweep them all the way to the other side, and then cut them into smaller elements, okay? So basically, you can create the object by sweeping a profile along some certain guides. This object is sweepable if it didn't have all of these holes, right? So not all the objects are simply sweepable because of the shape of them. For example, as I said, these holes here. So in the multi-zone method, what it does is, first, it tries to break the object into several sweepable bodies. And the object should not be very complex in geometry. So it breaks it into several sweepable bodies, and then what? And then in those sweepable bodies, you can use what type of element? Hex elements. So it tries to use more hex elements as much as possible into what? Into those sweepable areas. Now you might say, what is hex and what is hex dominant? Before I talk about hex dominant, let me talk about the method called patch conforming, which is another one of the methods that you have in general in ANSYS. So the patch conforming methods are what? Here you start your faces on the outside of the object with triangles and grow them inward to make tetrahedron. The good thing about it is it conserves the exterior shape of the object. So for example, if I have this simple or let's say the I-beam, for example, right? Let's say I have this I-beam, okay, which looks like this. So in this method, you start triangles on outside surface of the object, right? And then what? Then you grow each one of these triangles inward into the what? Into the depth of the object, and then you form a what with them? You form a tetrahedron with them, like this. Okay, you grow them inside. So you try to preserve the exterior surface of the object, and you try to basically approximate the object with a bunch of tetrahedrons growing inward. And as I said, the good thing is it preserves the outside shape of the object. Exactly opposite to that, we have the method called patch independent, where you start inside the object with a bunch of triangles and then you grow them outside to what? To form the tetrahedrons. Why should you do that? Because this method clearly would not preserve the outside shape of the object. Why would you do that? This is only good and useful when the shape of the object is very complicated. Okay, and the methods that are patch conforming, which is basically all of the methods except for this guy, any other method in ANSYS for meshing is a patch conforming method because they all try to preserve the exterior of the object. If those methods fail to achieve the results because the geometry is very complex, then you might go with this patch independent method and growing the triangles from inside and growing them out. Okay, that's like your last solution, last resort. So do not use this if any of these previous methods would be capable of creating a mesh. Do not go with patch independent. Now, what is hex dominant? Hex dominant is this. It uses these patch conforming methods first and creates all of these tetrahedrons. Then it tries to merge the adjacent tetrahedrons to form what? To form hex element. And since it might not be always possible to merge all of the tetrahedrons together, so you might have regions that are mostly hexa, right? They're hex dominant. So all of those regions are hex, but some areas that it could not merge, you might also have some tetrahedrons, okay? So you might have both, basically. So these are some methods that you have in meshing, and if you want to know where they are and how to apply them, here I'm going to show you. So what I will do is go here to the mesh and right click and say insert and then say method. And here you see the method is typically automatic. The software will decide for you, but if you want, you can force that method. So instead of automatic or tetrahedron, which I had right now, basically you might say, hey, could you make it hex dominant for me? And see what hex dominant gives you. Okay, so let me create that. Remember, it was all tetrahedron. Now you see, you clearly have what? You clearly have the hex elements here, but still you might have an area like this that you clearly see what here? You clearly see these tetrahedron elements. You see the triangles. But the rest of the object is mostly basically the hex elements. So that is called what? Hex dominant method. Or if you don't like the hex dominant method, you can go ahead and change it and make it a multi-zone or any other method that you saw over there. And the question is, what is the difference? I make a mesh and that mesh is going to what? Is going to solve the problem for me. So why should I change it to, let's say, multi-zone, right? What's the advantage? What's the disadvantage? Why do I do that? And the answer is the convergence, the speed of the convergence. Okay, so here is multi-zone that you can see. And let me talk about the convergence here. So if I look at the convergence, which we talked about, the speed of the convergence, as we increase the number of nodes, you clearly see that here, this top curve, which is the hexahedron, it is converging way faster than the tetrahedron or the prism elements. It is converging way faster than those to the final value, right? You see here at about kind of these many nodes, this curve is flattened out, while here, for this curve to flatten out, it takes probably, I don't know, this much. For this curve, it takes this much, and this guy is still there, still trying to go to a plateau, right? So, and the same thing happens if you look at higher order. So this is for lower and higher order elements, and I talk about them in a second. But it doesn't matter what type, what order of elements you use. The hexahedron elements always converge faster than tetrahedron. So if I can use a method like hex dominant, right, that gives me more hex elements, then I can make it converge to the final solution with a lot less number of elements, right? So if my method is hex dominant, then I don't need to go to size of 8 maybe, or size of 7 or something mil, maybe with 12 mil, with 15 mil or something like that. I'm still able to what? Get the convergence, okay? So your computation time is going to be saved for you. Now, since I mentioned that, let me also mention the lower versus higher order elements. So when you're looking in 2D or 3D, doesn't matter, you have lower and higher order elements. For example, if I look at 2D, I have this triangle, and then I have the same triangle, but the top triangle, which we call linear triangle, it only has 3 nodes at the 3 corners. While this parabolic or second order basically triangle, it has also nodes in the middle of the edges. So this guy has 3 nodes, this guy has 6 nodes. If you look at the square, this one has 4 nodes, this guy has 8 nodes. If you look at the 3D elements, the regular tetrahedron linear is 4 nodes, while this guy, you clearly see that it has what? It has 6 edges and then 4 corners, so it has 10 nodes, right? So clearly, because you have more data for interpolation of the values inside the element, the calculations of higher order elements are always more accurate compared to lower order elements. Okay, now of course higher order elements means more nodal displacement, means more computation time, but the results are going to be more accurate. Now, can I change this? Can I choose whether I want a linear or a parabolic element? The answer is yes, you can also choose that. Where is under mesh defaults element order? So if I want, I go here and let me delete this and go back to the regular tetrahedron, right? And let's look at the type of the order. So this is the mesh, this is the defaults, and here you see it says element order program control. So I can go ahead and say I want linear or I want what? Quadratic, and then that is where you can basically have more accuracy or less accuracy and less or more computation time. So as you can see here, whether I go with lower order or higher order elements, always hexahedron is converging faster than tetrahedron. So the suggestion is, if I want to put everything in a nutshell, if possible, go with hexahedrons. 1. 2, if you want more accurate results, especially inside the element, you need higher order. 3, if there is symmetry, take advantage of it. If there are details that are not going to affect the behavior of the part, remove them. For the mesh size, look at the convergence and look at the mesh metrics and make sure the mesh metric distribution is what you need and the results are converging. You can use adaptive mesh size. And if there are areas that are locally requiring a smaller mesh size, try to use mesh refinement and do not change the global mesh size. Okay, so hopefully these few important things will help you get better mesh results and overall get better final numbers, final calculations and charts. So thank you so much for your attention. I will see you in my next video.